entered the 20th century knowing that our world is situated in a vast sea of stars we now call the Milky Way galaxy. A sea that to all appearances was the entire universe. Then with the dawn of the great observatories, our views began to change dramatically. In 1918, astronomer Harlow Shapley jarred our sense of order when he calculated that our world is not at the center of this galaxy or island universe, but on its outskirts. From observations that followed, other astronomers learned that they had woefully underestimated both the size and content of the universe. They discovered that what lies beyond our sea of stars is not the void, but a universe immeasurably grand that challenges the imaginations of astronomers to this day.
It was known that there were these objects called nebulae, thousands of them, and that they were of different sorts. And one sort of nebula is just a word that means a fuzzy object, one sort of nebula were the spiral nebulae. And the great question was, are the spiral nebulae galaxies of stars like our own Milky Way, in which case we live in a vast, really an unimaginably vast and rich universe? Or are they just clouds of gas within our own galactic system, as Shapley had thought?
Harlow Shapley came to the National Academy of Sciences in Washington to argue for the immense universe that we were inside of, what we now think of as the Milky Way. And he believed that all objects that we saw, like these spiral nebulae out there especially, were members of our own universe, the Milky Way, as you might identify it, for want of a better term. Heber Curtis from the Lick Observatory surmised they were very far away, but his evidence was very weak. Some historians, of course, have looked at this debate as really a contest between the Lick Observatory in Northern California and the Mount Wilson Observatory in Southern California, who had, of course, two very different ways of looking at the universe.
The race was on to test Harlow Shapley's conclusion that our Milky Way galaxy was the entire universe. Some thought the famous astronomer might be wrong. Among these were Edwin Hubble and Milton Humason at Mount Wilson Observatory. Looking to the so-called Andromeda Nebula, Milton Humason, an assistant to both Shapley and Hubble, made the observation that would ultimately resolve the question.
Milton Humason was a high school dropout young man who'd knocked around California doing odd jobs, and he got a job as a muleteer helping to bring up the stuff from which Mount Wilson Observatory was built, and then as a janitor at the observatory, and then as what's called a night assistant, who's the person who runs the telescope and often feels that he knows more about the telescope than the astronomer does, and in Humason's case often was right.
Humason had taken the plates of the Andromeda Galaxy and went to Shapley and said that he thought that he saw a variable star in the Andromeda Nebula. Now, Shapley apparently took out his pocket hanky and erased the marks that Humason made showing this Cepheid star and said, well, that if that were so, if the Cepheid were present, it would mean that this nebula were very, very far away, and we know that can't be so. Now, a few years later, Humason worked for Hubble and did apparently the exact same experiment. Hubble listened to Humason this time and said, yes, the Andromeda Galaxy is very, very far away.
The real way to prove it was to find a kind of star in another galaxy that was like a kind of star that we'd found here in our Milky Way. And the kind that Hubble used most pointedly were the Cepheid variable stars.
Hubble found these pulsating stars, the Cepheid variables, that Harlow Shapley had seen in the globular clusters in our galaxy. Hubble saw those in Andromeda Galaxy. They were so very, very faint, and by measuring the period of light change in them, Hubble estimated that the Andromeda Galaxy must be 1 million light years away from us, much larger, much outside the space of the Milky Way galaxy.
When Hubble spotted that Cepheid, he was so excited that he took a felt pen and wrote VAR for variable right on the glass plate and an exclamation point next to it. It's one of the great historical documents of science, because with that observation was established the fact that ours was not the only galaxy, but that we live in a universe of billions of galaxies arrayed across enormous vault of cosmological intergalactic space.
Hubble was the first to show that our galaxy is just a mundane, ordinary object in the universe, nothing special, and that there were millions of these littered around the universe. So the last great step in the Copernican revolution, displacing the Earth from the center of the universe, the Sun from the center of the universe, and now the galaxy from the center of the universe.
A few years later, in 1929, Hubble discovered that not only were there countless other galaxies, but the universe was expanding. This time, crucial evidence came from the private observatory of Percival Lowell.
Percival Lowell employed an astronomer named Vestos Slipher to take spectra of the spiral nebula, which Lowell believed incorrectly to be planetary systems forming. When Slipher did this, he found that the spectra of most of these spiral nebulae were shifted toward the red end of the spectrum. He didn't know why, and he presented a paper saying, here's a result, I don't know what it means. Meanwhile, at Mount Wilson, Hubble took Slipher's list of redshifts and added some more of his own, started taking spectra of other galaxies, and found other redshifts even larger. And he realized what had escaped Slipher, which was that there was a relationship between the distance of the galaxy and the redshift of its spectral lines. The more distant the galaxy, generally speaking, the greater the redshift. This is what we know today as Hubble's law, and it's named after Hubble precisely because, although others had measured the redshift before, he was the first one to put together redshift and distance. And that is the fundamental observation from which arises the theory of an expanding universe.
The astronomical community generally responded to Hubble's work very enthusiastically, interpreting it mainly as evidence of an evolutionary universe. And it's remained that way ever since. There have been high points and low points, and of course one of the major issues is what is the value of Hubble's law, the numerical value, not the intrinsic value. And because that value, the quantified value of Hubble's law, which indicates the rate of expansion, is an indicator of whether that evolutionary universe is always going to expand, is going to eventually slow down, will eventually collapse on itself. Major cosmological questions that came out in the wake of Hubble's work.
When Hubble established that ours was one among many galaxies in a vast universe, this was a great discovery, one of the great discoveries in the history of exploration, and not just the history of science. Here, the depths of intergalactic space had opened up.
Once astronomers knew that there was much more to the heavens than the stars that surround us, they set out to observe and understand the galaxies that populate this new universe.
A galaxy is a large aggregation of stars. A typical galaxy, a spiral galaxy like the Milky Way, has 100 billion stars in it. Galaxies come in 3 different shapes, and they're classified just on the basis of their appearance. The dominant kind of galaxy is an elliptical galaxy, which looks to be round or sometimes slightly flattened. The other kinds of galaxies are spiral galaxies. Our Milky Way is an example of a spiral galaxy. And then the third kind of a galaxy is an irregular galaxy.
Most people are familiar with the spiral galaxies. Our own galaxy is a spiral, and so is the Andromeda Galaxy. Most of the visible matter is concentrated into a thin disk, showing a spiral pattern in the gas and in the stars. Spiral galaxies contain large amounts of gas.
Galaxies of the spiral type have a pinwheel type appearance. Now, if you look closely at a photograph of a spiral galaxy, what you discover is the whole galaxy contains stars, but that the spiral bands are distinguished by being brighter and bluer than the rest of the galaxy.
The second main class of galaxies are the ellipticals. Here the distribution of stars is more nearly spherical. In elliptical galaxies, star formation was very efficient. If you form stars efficiently, you use up the gas And since ellipticals don't appear to have much gas now, this is sort of an attractive aspect of the model.
Typical elliptical galaxies must have formed in a giant burst of star formation in which virtually all of the gas in the galaxy was used up in a single star-forming event which took perhaps 1 billion years, to which point the galaxy settled down to be an elliptical galaxy much like the ones that we see today. Spiral galaxies, for reasons that are only partly understood, formed their stars much more slowly. This allowed the spiral galaxy to condense into the disk that we see with the elliptical or halo or bulge component superposed on that disk. Irregular galaxies may be galaxies in which star formation has occurred very slowly over the history of the galaxy.
Irregular galaxies are very blue in color. Massive stars are very blue in color, but massive stars have very short lifetimes. So in a galaxy in which you see lots of blue light, obviously if the stars have short lifetimes, they have to have been formed recently. So stars are forming randomly over the face of irregular galaxies at pretty good rates today.
Normal galaxies were quite well classified by Edwin Hubble earlier on this century, and he developed a sequence of galaxies that was called the Hubble sequence. We now know, in fact, that what he was describing were actually giant galaxies like our own. We live in quite a big galaxy. And we've recently realized that for every big galaxy like ours, there are, in fact, maybe 10 dwarf galaxies. So our picture of the universe of galaxies has actually been changing over the last couple of decades.
Hubble's tuning fork diagram, which sorts galaxies into a sequence by means of their appearance or their shape, was thought by Hubble to be an evolutionary sequence, and now we don't believe that's true, because it turns out each of those kinds of galaxies contains old stars, which appear to be equally old. It looks as though all galaxies of all those different shapes were born each at the same time.
Most galaxies started to form at about the same time, say 15 billion years ago. In the case of ellipticals, by 14 billion years ago, that was it. There was no more star formation. On the other hand, in irregular galaxies, the rate of star formation has remained essentially constant over the whole 15 billion year period, so that the oldest stars in just about any kind of galaxy you look at carefully have the same age.
Hubble believed that galaxies formed continuously in the universe and slowly changed from one shape to another as they age. However, the discovery that virtually all galaxies were born at the same time proved this idea wrong. What then brought about the diversity of shapes that astronomers see today?
One of the raging questions in the theory of galaxy formation concerns what we call nature versus nurture. Which of the properties of the galaxies were associated with their initial formation, and which had to do with their environment?
We believe that most of what a galaxy looks like was a feature of the galaxy at its birth. So an elliptical galaxy is born as an elliptical galaxy. A spiral galaxy is born as a spiral galaxy. An irregular galaxy is born as an irregular galaxy, except that as we find in the middles of clusters of galaxies, where galaxies can collide with one another, their shapes can be affected by collisions.
When one takes deep exposures of distant galaxies, many of the more vigorous galaxies are in a state of merging together with other galaxies. Clearly, their environment is causing them to display their present characteristics, and beautiful simulations have been done on computers that show that when galaxies merge together, they can develop beautiful spiral features for a while, and then much, much later in time, the spiral activity may die down and the merger will result in a beautiful elliptical galaxy. So environmental effects such as mergers and collisions between galaxies lead to the way they are.
We see galaxies whose appearance, whose shape, is so disturbed as to suggest that a collision must be occurring. We see evidence that the collision has occurred because a starburst is going on. A starburst galaxy is a galaxy which is currently forming stars at a prodigious rate.
One mechanism for stimulating this starburst mode of evolution is when galaxies collide or interact gravitationally. In the extreme case in which galaxies will actually collide with one another, then the idea is that the giant molecular clouds, the regions where the density is high enough and the temperature is cool enough for star formation to occur, these giant molecular clouds can actually bump into one another. And via the shock waves, the gravitational instability will cause the center core of the cloud to begin to collapse. That core will increase in density, will fragment. Those fragments will go on to collapse and form individual stars, and a new star formation region will turn on.
One of the most compelling pieces of evidence that a collision must be occurring is that in the central regions of clusters of galaxies, great conglomerations of galaxies that are all moving around like bees in a great swarm of bees, collisions are able to occur much more frequently just because the galaxies are very much closer together. And in the central parts of these great clusters of galaxies, one finds huge elliptical galaxies, giant elliptical galaxies that apparently are galaxies that have eaten lots of other galaxies during the course of time. And a lack of, say, spiral galaxies in that particular region, suggesting that indeed this galaxy has been eating other galaxies.
We find that more and more galaxies and groups interact and make interesting merged forms. Every once in a while, a rather unequal merger can occur, where a smaller galaxy in a cluster gets swallowed by a larger one, and we have a form of merger which we call galactic cannibalism, where one galaxy swallows another for lunch. Understanding more about these interactions among galaxies is perhaps the most exciting area of extragalactic astronomy, and it's going to be where I think a lot of the progress is going to be made in the future.
Galaxies are not island universes as once was thought. They swarm within clusters and sometimes collide. Even our own galaxy, a member of a cluster known as the local group, silently moves among its neighbors.
There are about 20 galaxies in the local group. The local group seems to be in two big pieces. Each one is dominated by a big galaxy. Our piece with the Milky Way is more or less the focus. And then the second piece is dominated by our nearest big neighbor in space, the so-called Andromeda Galaxy, or M31. And each of those two big galaxies has companion galaxies that are orbiting around them like the Earth orbits around the Sun. The total size of the local group is about 3 million light years across.
If you think of the Milky Way galaxy as a grapefruit, Andromeda, which is the nearest large galaxy, is only 20 grapefruit diameters away. It's another grapefruit, 20 grapefruit away, which means then that if you superimpose a random motion on these galaxy grapefruits, there's a very high probability that galaxies will collide with one another.
Our local group is one of those groups that's just in the process of forming. When we look out and see our neighbor M31, we see that it's approaching us with a velocity of a few hundred kilometers a second. In something like 4 or 5 billion years, M31 and our galaxy will pass close to one another. We don't know. It's possible that the two galaxies may merge at that point to make one bigger galaxy. It's also possible, though, that they're going to pass sideways and will remain in orbit about one another like this for a very long period of time. It's hard to say.
Yet the stars inside the galaxies are so distant from one another that galaxies tend to move through each other without many star-star collisions, if any. And so the end result is that the overall shape of the galaxies, which is defined by the gravitational field of the entire ensemble of stars, can be distorted by the close passage or collision with another galaxy.
Now, around the Milky Way, we have our own companion galaxies known as the Magellanic Clouds. In a recent measurement at Lick Observatory, the sideways motion of the Large Magellanic Cloud was detected around our galaxy for the first time. From that, we can calculate the whole orbit of the Magellanic Cloud. And we now know that over time, The Magellanic Cloud is going to spiral into the Milky Way, and in a few more orbital periods, the two will merge to make a slightly bigger Milky Way.
And up we go.
Gravity, that familiar force, orchestrates movements within our local group. It also organizes galaxies on an even grander scale. And so astronomers scan the universe for its cosmic design.
Galaxies are not distributed uniformly through the universe. They occur in clumps. When you find one galaxy, you're likely to find several more in its neighborhood. Galaxies may coalesce in clusters containing anywhere from a handful to several thousand galaxies in the richer clusters.
If you were out floating in space, you'd see mainly galaxies separated by vast, empty, dark spaces. And we used to think that that distribution was fairly random, that there were a few great clusterings of galaxies, but then in between, galaxies were strewn fairly randomly, spattered across space. But the great discovery of the last 10, 15 years is that that structure, the way galaxies are arranged, is really very patterned. It's not exactly regular pattern like a checkerboard, but there are chains and strings of galaxies, and it's almost like a lace, or some sort of irregular lace or a tapestry in which galaxies are arranged.
The last 2 decades have seen a real improvement in the quality of our detectors that we put on our telescopes. And with these more sensitive instruments, we can survey a much larger region of the universe around us.
Yeah, the shroud is sort of covering most of the instrument. This instrument is called COSMIC, the Carnegie Observatory Spectroscopic Multi-Slit and Imaging Cameras, and Bill Kels and I spent the last 3 years building it. So down there is the aperture wheel, and that's the thing that holds those little masks that allows the light from certain galaxies to go into the instrument and excludes the light from all other areas. Then a camera lens re-images the spectrum of all these galaxies onto a detector. It's about 2 inches square, a piece of silicon, kept very cold with liquid nitrogen because all the signals we're looking at are very, very faint. Not my favorite thing in the world, coming up and down here. But that's how you have to do astronomy.
Many groups are making surveys of the distribution of galaxies in our vicinity. What we see in these surveys is larger and larger structure, it seems almost without limit.
We call the biggest units of galaxies superclusters. They are places where there are a few rich clusters and then a high density region, an envelope of galaxies around them. And then the places in between the superclusters are called voids. They're almost like oceans, devoid of galaxies.
From the distribution of galaxies, clusters, and superclusters, astronomers have begun to develop models that define the large-scale structure of the universe.
One model which is popular is the so-called bubble model, in which the galaxies are arranged on thin walls, rather like bubbles in a foam. And the voids are like the interiors of the bubbles. And when the walls intersect in a foam, there can be places where there's sort of a node where walls come together. We tend to see our big superclusters located at those intersections.
We think we have the fundamental understanding for how this cosmic hierarchy of structure formed, namely through gravity. Gravity is a long-ranged force, but it falls off with distance. And because gravity is stronger between objects that are closer to one another, it's very natural that the galaxies would tend to congregate and cluster most strongly on the smallest distance scales.
The local group seems to be on the outskirts of a supercluster of galaxies. And this supercluster is just in the process of forming. And its extra matter is decelerating the motion of everything in its vicinity, including our local group. So we're still moving away from the center of this supercluster, but we're being slowed down. And at some part in the future, we will reach some maximum value and fall back in. This entity, which we are members of, is called the Great Attractor. Well named because it is in the process of attracting and decelerating all the galaxies in the neighborhood.
The Great Attractor is a continent of dark matter with some galaxies overlying it or spattered through it. It's a concentration of matter that is so much greater than average in our region of the universe that our galaxy and other galaxies around us are streaming toward it. Now the universe is expanding, but this higher concentration of matter is retarding the expansion somewhat, and that's how we detect it.
Why are galaxies in the universe distributed in these clumps with big voids between them? We now understand that rather well. This has been one of the big breakthroughs in extragalactic astronomy in the last decade or so. Our picture is that the original Big Bang, the expanding universe, early on was rather smooth, but contained very small density fluctuations in it. Just tiny ones, 0.1% or 0.1%. Small as they are, they cause the clumping that comes later, because each one of those density peaks has a little bit of extra gravity that retards and slows down the expanding universe. And as time goes by, it pulls all the surrounding matter into it.
So, what we once thought was a void turns out to be filled not just with other galaxies, but billions of them, woven into a lace of clusters and superclusters. Together, these galaxies reveal the grand design of the universe, a design we are just beginning to fathom.